It's my good pleasure to come to talk with you. I'm Wang Zhengguang, O Zhengguang. Before I kick off, I'd like to first have a question for you. How many of you have been interested in edge intelligence? A lot of you, you're really ahead of curve. Indeed, edge intelligence is a new topic in academia, in vertical, but actually it's somehow still new in vertical industries. I'm O Chengguang. I'm from Edge AI team from Huawei Cloud Edge Cloud Innovation Lab, where focus is on Edge Cloud and the key technologies and the challenges in Cloud Edge, as well as low-hanging fruits. Today I will share with you something on a vertical line and its innovation in the Cloud Edge. Previously, I've been working on the cloud computing and edge and cloud computing, and I'm now responsible for center development and operation. I'll cover 4 parts in my presentation. I'll start with challenges, as well as what is Edge AI, and what deserves our research and what to be coped with. Second, I'll share with you what we've done in CubeEdge community, the status quo of AI-SIG, its operation, and its target. And third, I will walk you through CeDNA architecture and features. Last but not least, I'll present the following a roadmap of CeDNA. This one elaborates Edge AI scenarios. But before I come to that, I would like to talk about what is AI of Edge. So the prerequisite of this one is edge computing. But what is edge computing? I think it's necessary for me to stress that one important feature of it is around cloud. It centers on cloud. Only when you have a hub cloud, you can do edge computing. Otherwise, you can't do that. Or you might refer to other scenarios as embedded scenarios. That's why to articulate Edge AI, I have to do some comparison with 2 things. The first one is about the cloud intelligence, which centers on cloud. Second one is about embedded AI. So later I will touch upon that to give you a sense about what do I mean by that. Let me start with application scenarios when we have a smart home. Like there's a detection of falling elderly as well as the crying of babies. That's all relevant to intelligence. And the second is about the smart healthcare. It's about smart diagnosis. In smart cities, we see, for example, those municipal management for those unlicensed running of business along the roads. The fourth one is AR, VR, because there are many data to be transmitted. Is it possible to use AI to compress data and then reconstruct those data into high precision, high definition data at devices, and that will drive down the cost. That's also a kind of scenario of Edge AI. And next one is intelligent transport, industrial internet. Talking about intelligent transport means those smoke detection in tunnels as well as reverse driving or the wrong driving detection, and industrial internet, for example, detection of electric circuit boards. And next one is about smart agriculture. I'm not sure whether you know that, for example, we use drones to try to provide those things or materials to grow the crops, or just spray pesticide. It's possible to identify weeds and spray pesticides. Then that would be really productive. And then, for example, last one is about those robots in retails. For example, they can do the delivery of food or the guidance of those consumers. So there are many use cases today. Talking about all of that, so how about the trend in industry? In 2019, Ghana's production, there was such a curve of Ghana. Fusion AI has been climbing up. The day before today, IDC and Forest issued technology production 8 trends of 2020. 2021, and you can see that Edge AI tops the list. In particular, the combination between Edge and AI. Besides, Huawei Cloud and our competitors have all unveiled the relevant products related to Edge AI, but they are still in infancy stage. Its security, performance, cost are still to be or can be improved. We just talk about the concepts like Edge AI and Embed AI. But what are differences between cloud intelligence and Edge AI? When talking about cloud intelligence AI, so because you put everything on the cloud, it's easy to have latency and cost. That's quite an obvious challenge. But what is embedded intelligence? Like at the entrance of the campus, it's necessary to recognize license plates of cars. But the challenge is that they will never update the software running in the equipment of the detector for 1 or 2 years. So that's why the challenge is about how can you really run the system with the minimum cost. So this is something that will be researched. By combining Edge AI and the cloud, by collaborating those two factors, and we believe it's possible to cope with the above-mentioned challenges. When talking about Edge AI, what are specific or what challenges are specific to Edge AI? The first, heterogeneous software and hardware. We all know roughly 3 years ago, Huawei unveiled Ascend 310. Baidu Kunlun was released last year, and Cambrican as well as Yun Tianlifei all released their AI accelerator chips for Edge. Each vendor has unveiled something themselves. We also see AI frameworks like MindSpore, TensorFlow, Paddle, and I don't list some of them here, but those are mainstream ones. And when we're in the system of heterogeneous software and hardware, how can we ensure consistent experience of customers? By only calling API one time, is it possible to just call or manage a large number of applications? I think that's that is the biggest challenge ahead of us. Second, about limited edge resources. Usually hardware is running in the box. The cost of hardware will definitely more expensive than centralized solution. So with limited resources, how can you do more? Or how can you run more tasks? That has brought us a big challenge, besides, your hardware may just put in place roadside, like 2 years ago. For example, we talk about the removal of those tolling stations across the provinces or near provinces, and there were a lot of boxes installed along the road of those provincial highways. So the environment of those hardwares are really bad. And besides, actually we may have some computing devices to serve as MEC edge nodes in the 5G base stations or cabinets, and then how to power them. And there are a lot of constraints related to power consumption as well as the infrastructure, like water and other resources. So there are a lot of resources constraints for edge. And next one is about heterogeneous edge data. But I have to address this one from two perspectives. The first one is about time, and the second one is about space. What do I mean by that? For instance, we have 4 seasons. When cameras take picture of background, it's different. Mostly green in spring, the black, white, or gray in winter mostly. So you see the variance of colors in different seasons. What do I mean by spatial differences? And it means the gate of or the entrance of the eastern campus is different from that of the one in the west, because there are different dimensions and data layout is different, or data distribution is different. So compared with those data gathered at your home office, because if you use that model to train the data to train the models, the training results will be different in different scenarios. Because that's a very acute issue once you download the models and their environment of training is all different. And fourth one is about small data sets and the model code start. What do I mean by that? The previous one is what I call data drifting, or model drifting. And what is small data set? When I visited the production line in Dongguan, because there are a lot of abnormal things happening across board. Like, for example, there would be the rolling part, or there could be some unsmooth part on the board. But those kind of abnormal things may occur only one time a day. That's why we call them small data sets. It means if you want to train data, it would take a very long time. And that will also cause a problem of model cold start. And last one is about privacy and security, because you don't want to have the data flow to outside campus. And how can you really address the concerns of the users and protect privacy of the users? So I would like to use some typical edge AI scenarios to elaborate on that. So this one is safety helmet detection. For example, how does it look like when you detect those helmets? For example, in foggy days, rainy days, a strong light, and at construction site when there's any light at the construction line during night, and you might have a disruption of the sharp rays of lights, or installation angles differ from each other because of the distance between the camera and construction sites. It is estimated is about 5% or 10% accuracy gap.
So I've been involved in CubeEdge community Currently in Cube Edge, there are a lot of users who are running their AI applications on Cube Edge. Running AI applications on it may bring a lot of issues such as usability, performance, and other things. We've been focusing on this direction. I think it is necessary for us to do one thing, to collaborate with the community to address the challenges faced by edge computing. So we've referenced the operation mechanism of CNCF. So we're using the SIG, Special Interest Group. We established the SIG in the end of last year. Now we have over 300 people in our WeChat group. We have regular weekly meetings. 10 o'clock every Thursday morning. Apart from the regular meeting, we also have offline in-person meetings. We have meeting minutes to track the progress of each topic, to make sure the topic is included in our roadmap, etc. So this is how the SIG is running. From the end of last year until last month, we agreed that edge cloud synergy may be a good way to address those challenges. Therefore, it is necessary to focus on this direction. People all agree that we can leverage edge cloud synergy to provide an edge AI platform that features cost effectiveness, high performance, ease of use, and privacy protection. Once we have the goal, we agreed upon 4 directions. First, automated adaptation to heterogeneous edge resources. We want to use the abstraction layer to facilitate the management of heterogeneous edge resources so that the management and the maintenance efficiency can be improved. We need to do all kinds of things, for example, interconnection between different frameworks and hardwares. Second, we need to realize a basic edge AI framework so as to achieve the unified management over dataset models, including cross-edge data synchronization and unified configuration. Number 3, by using device edge cloud collaborative training and inference to efficiently use all kinds of resources. We have different kinds of resources and with a different computing power. If we can fully use these resources, then we can achieve device edge cloud collaborative training and inference. Number 4, this is more specific. This is about incremental and lifelong learning. This kind of learning can address the issues such as insufficient data samples and non-IID data. Our ultimate goal is to achieve smarter edge AI over time. For example, in the context of a spring season, then the model should be able to be refined according to the context of a spring season. And the edge AI can become smarter over time. This is the overview of CeDNA. At the bottom, this is the support for all kinds of hardwares. I mean AI acceleration hardwares based on Kubernetes and Edge. We have edge nodes management, application management, hardware resource management, and cross-edge traffic governance. This is a kube-edge infrastructure capability, and on top of that, we built AI framework, cross-edge dataset management, collaborative inference, incremental learning, and lifelong learning. And on top of that, we want to provide APIs with good usability. It may call or invoke Kubernetes APIs. We want to provide some APIs for the AI developers. AI developers, they do not need to understand the specifics of concepts in Kubernetes. For example, deployment or port, they only need to provide or submit the script. Then they can achieve the edge AI application. We will interconnect with mainstream AI inference framework. Such as pre-training model, smart labeling, model conversion, model compression, and data pre-processing. These capabilities were already in place in AI ecosystem, and there's no need for us to change them. We only need to reuse them and leverage their capability to fast build the AI capability. And based on this entire system, we can work on the edge intelligence scenarios. We can find out the special issues in those scenarios so that we can help the developers and users feel the benefits from Kubernetes AI. We're now working with partners from the community on some cases. If you're interested in that, you're welcome to participate in our community regular meeting. Usually we have very heated discussion each meeting. Usually the meeting would last for 2 hours, but actually the meeting will go beyond 2 hours, up to 2.5 hours or even 3 hours. So I talk about what is edge AI and what are the challenges, the things that we've done in the community, and how people are working together to address those challenges. Concerning CeDNA, this is the achievements we've made. In March, we released a version. Let me talk about CeDNA. The meaning of this name. It is a part of the solar system. It is at the edge of the solar system. So it represents the edge intelligence. So it would leverage the edge cloud synergy to achieve the best results of the AI algorithms. As you know, we have very strong computing power, and usually at the edge it is used for inference. It has limited resources or computing power. But we want to use edge-cloud synergy to power the AI framework. We have a global manager. This is a component. This is used for AI task management, AI task coordination, including creation, update, lifecycle management. Second, it can coordinate the tasks between edge and cloud. So it will know which tasks should be coordinated. You also need to manage models and data sets. A shared storage is used. Put the data in a shared storage pool. Edge only need to put the data into the pool, and other parties who want the data, they only need to fetch the data from the pool. At each node, including cloud node and edge node, there is a local controller which can manage the end-to-end local processes. It can also manage local models and data sets. The third component is worker. Worker contains training and inference tasks. It is corresponding to the container in Kubernetes. So training and inference tasks are done in worker. There is a lib library in worker. It provides APIs. It implements some algorithms. It will decide when the data should go to the cloud, when the data should be interacted with the cloud. So generally speaking, this is the framework of CeDNA. This is a basic framework, and on top of it, we've done several things. We've done edge cloud collaborative inference. The goal of inference is that with limited edge resources, we want to improve the inference performance. Usually, this is used in the scenario of intelligent cameras with limited computing power. But if those cameras want to do more complex tasks, for example, they want to do a detection of the safety helmet, in that context, the helmet is a small object, it's far away from the camera, and the color is very similar to the background. In that case, it's hard to detect the object. It cannot run a very complex algorithm. So how to handle that? We can use the edge cloud collaborative inference to deal with that. In each edge, there is a small model. It will be processed locally. The data will be pushed to the small model for local processing. And then it will go to the lib library to determine whether it will need to go to the cloud for further processing. Then in the cloud, there is a deep model. which is a bigger model, which is more complex, which can handle more complex scenario.
After decision making by inference, results will be returned to edge by comparing the result. If it is good, it will be forward to front-end applications. It's quite straightforward and simple idea, but it's quite efficient. That can help us to address resources constraints at edge and also complexity of handling. And it's not that costly. Usually, a big model in the cloud may have a lot of edges. So that is about inferences of edge. And then we also need to talk about collaboration between edge and cloud. First, in big network, we will detect objects, and then we will assign tasks to them, and then we'll have a collaboration between them. We'll have an edge-edge collaboration. This is now what we are designing together with the edge. So next one is about edge cloud collaborative incremental learning. Applications at edge can be adaptive to the context incrementally, making the whole decision more accurate, and that will help us to address independent distribution challenge. So in some cases, for example, smart traffic, there are a lot of long-tail protocols, algorithm. For instance, smoke detection tunnels is similar to license plate recognition and facial recognition. They're seldom used. It's hard to gather data for those rarely happening scenarios. So that's why we think usually the accuracy is not very big. 70 or 80% are really good enough already. In that case, is it possible once we push model to the edge and the context, in the context related to edge, we may collect relevant data and we may collect samples. We use that sample to train models to make the whole training more accurate. So this is about incremental learning. The main idea behind this one is that, so first, the data and samples will be sent to the edge. Algorithms in lib library will check about or detect, try to verify the results of inferences if it believes it's not that good or if it's not up to our bar. If we think inference is not that good, we will put it to the cloud. And the cloud actually will use this application of inference. Once data is all sent to cloud, I may have incremental training for models as well as those migration learning training for models. But we need manual labeling, which is still a thorn issue in the industry. Once data labeling is down, once retraining is down, and then we will send it to the ad, and that will be an iterative incremental learning. So the current incremental learning is quite basic. We can only achieve very simple incremental learning, but we have a multiple task incremental learning to make it even better. In the future, in the community, we're still discussing, so how about our policy of data gathering or sample gathering? Is it possible for a system to collect the most efficient samples to enhance incremental learning? This is ongoing discussion in the community, and we might see some results in the second half of this year. what we are discussing about how to lift it to another level, but we've already amassed some fundamental technologies. So next one is about federated learning. As you know, this is a design to solve one thing without having data leaving the campus, because data is supposed to be at edge in edge computing. That's why the combination between edge computing and federal learning is quite natural. The combination can help us to solve fifth challenge, which is related to security. The idea of this federal learning is that each edge will be trained. Parameters, weights, after training will be sent to cloud, and the cloud will do aggregation. It's not necessary to store data in the cloud, but it's still possible to get a sound model. It's applicable to industrial internet because first, enterprises owner do not let their data leave the campus. And second, data amount in an enterprise or at production lines are limited. If it is possible to use federated learning, and then it's possible to train a good model. So this is all about federated learning. But of course, we are still having a team studying federated learning, including someone from Toronto University, as well as partners and users, and they are now talking about what should be done in the next stage. Suppose there's a huge amount of data at one node, but not much another node. To run federated learning, how can we ensure the results will not link to the node with more data samples? So this is to solve bias issues. And besides, and how to process batch data, because after training, it's really hard to input all of those large amount of data into the learning. That will really slow down the whole processing. So those are the discussions we are having today. Last, I'd like to share with you from perspective of developers how to use it. Our belief is that the existing framework, algorithms, technology stacks of the users will not be changed, will remain the same. Users only need to add a small amount of codes, and then they could enjoy the benefits of Edge AI. So this is the idea of our design. Developers only need to load lib library. Only by leveraging the previous algorithms and capabilities, after loading lib library, it's possible to have collaboration between Edge Cloud. This is about case how to use Edge Cloud collaborative inference and incremental learning. We see 40% of precision improvement. Left-hand side, you see someone is wearing a casual hat who is not detected, but he was detected after the collaboration of the Edge and Cloud. And on the right-hand side, and the casual hat was misrecognized as safety helmet. So such a technology helped us detect this person. I'd like to share with you some roadmap. In March, we released a version, and we built the basic models and frameworks. On top of that, we add federated learning, collaborative inference, incremental learning. And then in Q2, we will add lifelong learning, transfer learning. What is lifelong learning? It means system will learn like human does. Let's say I learn a cat is an animal, and then when I see a dog, I know it's an animal as well. But can we have the same thing happening to the system? Because human can abstract knowledge and store in their brain. Likewise, AI knowledge can be stored in a knowledge base or database. When there's new incoming knowledge, and I will do query to see which one is most similar one. If I get some results, and I will also add this new knowledge and accelerate the learning. It means the previous samples as well as the parameters of models can be reused to accelerate the learning target. So this is what do I mean by lifelong learning, and we'll see a release in June for this lifelong learning. And then we also later have, for example, collaborative inference between edge and edge cloud collaborative tracking. It means through multiple edge, I track a single one object, which is boiled down to VID. By achieving collaboration between edge and cloud, we can enhance EID's algorithms and the whole efficiency of system. We're now designing this solution. And the fourth milestone is that we will have optimization for automated edge model. You know, architectures and the computing operators as well as memories are all different across edge nodes. Is there any way for me to really automatically optimize and price the most suitable edge model that fits a node? That's a very interesting topic. And last, we also integrate with Huawei Cloud IEF. If you are interested in those commercial as well as a large-scale commercialization, an application of the solution, and then we can do it help. So what I introduced include scenarios, values, as well as technical challenges of edge AI and its difference from traditional offline AI and cloud and AI, and then what CeDNA is and how it can be used to develop applications with edge cloud collaborative AI capabilities. The first link is our project's address. And second, you may have access to Slack channel. Left-hand side QR is our container metric cubes, social media account. You may get some materials from us. On the right-hand side, that was for interactions. So this is about our curriculum. Thank you.